What if everything we know, every star, every galaxy, even the vast expanse of the cosmos itself, is just a tiny speck in something far grander? Picture this. You're standing at the very edge of the observable universe, where the light from the farthest reaches of space finally reaches your eyes after traveling for billions of years. But here's the haunting question: what lies beyond that edge? Is there simply nothing, an infinite void? Or could there be realms so strange, so unimaginable, that they defy everything science has taught us? This is the mystery that has captivated astronomers, philosophers, and dreamers for centuries, and today we're going to explore it together. The universe, as we understand it, stretches an astonishing 93 billion light-years across. Yet, that's just the part we can see. Beyond that boundary, the rules of physics as we know them might not even apply. Some theories suggest parallel universes bubbling into existence, while others propose cosmic membranes colliding in dimensions we can't perceive. And then there's the spine-tingling possibility that our entire universe is just one tiny pocket in an endless multiverse, where countless other realities exist alongside ours. The sheer scale of these ideas is enough to make your head spin, but that's exactly why this question is so electrifying. It forces us to confront the limits of human understanding and wonder. Are we alone in this cosmic ocean, or is there something or someone out there gazing back at us from the other side of the edge? This journey won't just take us through the cutting-edge science of cosmology. It'll challenge us to think bigger than we ever have before. We'll dive into the theories that push the boundaries of physics, from the holographic principle to the mind-bending concept of eternal inflation. Along the way, we'll meet the brilliant minds who have dared to ask these questions and the startling answers they've uncovered. So if you've ever stared up at the night sky and felt that tug of curiosity, that whisper of wonder about what might lie beyond the stars, you're in the right place. Buckle up, because we're about to venture into the great unknown, where the mysteries of the cosmos await. 93 billion light-years, that's the staggering diameter of our observable universe, a bubble of space and time containing everything we've ever seen or detected. But here's the catch: this boundary isn't a physical wall or some cosmic fence. It's simply the farthest point from which light has had time to reach us since the dawn of existence, roughly 13.8 billion years ago. Think of it like standing on a vast, foggy plain. The farther you look, the hazier things get, until eventually, the fog becomes so thick you can't see past it. That's our cosmic horizon. Beyond it, galaxies might exist, whole civilizations could thrive, but their light hasn't had enough time to cross the immense gulf of space to reach our telescopes. So what does that horizon actually look like? Surprisingly, it's not darkness. Instead, we're surrounded by the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself. This ancient light is the oldest signal we can detect, a snapshot of the universe when it was just 380,000 years old. But beyond that, the universe could stretch on indefinitely, or it might curve back on itself in ways we can't yet comprehend. Some theories even suggest that space-time becomes so warped near the edge that the laws of physics as we know them break down entirely. This raises a profound question. Is the edge of the observable universe the true limit of reality, or just the limit of our perception? Imagine a ship sailing toward the horizon on an endless ocean. Just because the crew can't see land doesn't mean there isn't more ocean, or even other continents waiting beyond their view. In the same way, the universe might extend far beyond what we can observe, with structures and phenomena so alien they'd rewrite our understanding of existence. The only way to know for sure, keep exploring, keep questioning, and keep pushing the boundaries of what we think is possible. The Big Bang wasn't just an explosion, it was the birth of space and time itself. Picture this, a single point of unimaginable energy, smaller than an atom, suddenly expanding faster than the speed of light. In less than a trillionth of a second, the infant universe grew from microscopic to cosmic proportions, creating the fabric of reality as we know it. But here's the mind-bending part. If space itself is stretching, what exactly is it stretching into? Scientists call this the embedding problem, the idea that our universe might be expanding within some larger, unseen structure. One leading theory suggests higher dimensions, realms beyond our familiar three of space and one of time. Imagine a sheet of paper floating in a vast room. To a tiny ant crawling on that paper, their world appears flat and two-dimensional. They'd have no concept of the room surrounding them or the third dimension stretching upward. In the same way, could our universe be like that sheet, existing within something far greater that we simply can't perceive? Then there's the multiverse hypothesis, which proposes that our universe is just one bubble in an endless cosmic foam. Each bubble might have different physical laws, different constants of nature, even different versions of reality where every possible outcome plays out. It's like a cosmic version of a soap bubble bath, where new universes constantly form, collide, or drift apart in ways we can't yet detect. Some physicists even speculate that these bubble universes could brush against each other, leaving faint imprints in the cosmic microwave background, ghostly fingerprints from neighboring realities. But perhaps the most radical idea comes from string theory, which suggests there could be as many as 11 dimensions curled up at scales so tiny they're invisible to us. In this view, what we call the edge of the universe might just be a fold in higher dimensional space, like the edge of a shadow on a wall. The true nature of reality could be far grander than we've ever dreamed, a vast, multidimensional landscape where our entire cosmos is just one small valley. This leads us to an even deeper question. If space is expanding, does it have an edge at all? Some models suggest the universe might be infinite, stretching forever without boundary. Others propose it could curve back on itself like the surface of a sphere, travel far enough in one direction, and you'd eventually return to your starting point. The truth is, we don't know yet. But every new discovery, from gravitational waves to quantum fluctuations, brings us closer to unraveling the greatest mystery of all: what lies beyond the limits of our cosmic horizon. Cosmic inflation might sound like a simple idea, space stretching outward, but it's one of the most radical concepts in modern cosmology. Picture a balloon inflating at speeds beyond comprehension, doubling in size again and again in fractions of a second. That's what scientists believe happened to our universe in its first sliver of existence. But here's where things get truly bizarre. If space was stretching, what exactly was it stretching into? The answer might upend everything we think we know about reality. One school of thought argues there is nothing beyond, not empty space, not darkness, but literal nothingness. No dimensions, no time, no physics, just a void so absolute that the word beyond loses all meaning. In this view, the universe isn't expanding into anything. It's creating space as it grows, like a painter adding new canvas while working. But others propose something far wilder, that inflation never truly stopped. Instead, it's still happening in pockets beyond our cosmic horizon, birthing new universes like soap bubbles in an infinite froth. Each bubble could have its own laws of physics, some where gravity is stronger, others where time flows backward, or where matter behaves in ways we can't even describe. Then there's the holographic principle, which suggests our three-dimensional universe might be a projection from a two-dimensional surface at its edge, like a cosmic version of a movie screen. If true, the edge we're searching for could be an illusion, a shadow of deeper processes playing out in a reality we can't access. It's as if we're characters in a video game, unaware that our entire world is just code running on some vast, unseen computer. But perhaps the most startling clue comes from quantum fluctuations, tiny ripples in the fabric of space-time left over from inflation. These ripples eventually became the seeds for galaxies, but they might also hold fingerprints of what lies beyond. Some theorists speculate these patterns could reveal collisions with other universes, like cosmic bruises from a long-ago encounter with a neighboring reality. If we could decode them, we might finally catch a glimpse of the greater multiverse lurking just out of reach. So is the edge of our universe a boundary, a gateway, or just a trick of perspective? The more we learn, the clearer it becomes that the answer might lie not in the stars, but in the very nature of existence itself. Galaxies aren't just drifting randomly through the cosmos, they're racing towards something. And not just any something, but a gravitational pull so colossal it defies explanation. Scientists call this eerie phenomenon dark flow, and it's as unsettling as it sounds. Imagine throwing a handful of leaves into a river, only to watch them all swirl toward a hidden current you can't see. That's what's happening to entire clusters of galaxies, all streaming in the same direction at breakneck speeds, as if drawn by some unseen hand beyond the edge of our universe. The numbers are staggering. These galaxies are moving at nearly 2 million miles per hour toward a region of space with no known massive structures, no superclusters, no cosmic voids powerful enough to explain the pull. It's like standing on a beach and feeling the tide drag you toward an ocean that shouldn't exist. Some researchers believe dark flow could be evidence of something extraordinary. Other universes lurking just beyond our observable horizon, exerting gravitational influence on ours. Picture a chain of islands in an endless sea, each with its own unique landscape, separated by waters too vast to cross. If that's true, our universe might be just one island in an archipelago of realities, each tugging on the others in ways we're only beginning to detect. But there's another possibility, one that's equally mind-bending. What if the Big Bang wasn't perfectly uniform? Tiny asymmetries in the early universe could have left behind imprints, like cosmic fingerprints, warping space-time on scales so vast they're still shaping galactic motion today. Or perhaps dark flow is a sign of something even stranger, a flaw in our understanding of gravity itself. Einstein's theory has held up for over a century, but what if, at the very edges of existence, the rules start to bend? The most tantalizing clue comes from the cosmic microwave background, the afterglow of the Big Bang. Subtle distortions in this ancient light seem to align with the direction of dark flow, as if something massive, something beyond our universe, left a shadow in the fabric of reality. If that's the case, we might be staring at the first evidence of a multiverse, a realm where other cosmic bubbles brush against ours in ways we can barely comprehend. So is dark flow a cosmic mystery or a cosmic clue? The answer could rewrite not just our maps of the universe, but our very definition of reality. And as telescopes grow more powerful and probes more precise, we might finally catch a glimpse of what's pulling us into the unknown. Until then, the question lingers like a whisper at the edge of space. Are we alone in this vast expanse, or is something out there, something unimaginable reaching back? The idea of multiple universes isn't just science fiction. It's a serious scientific possibility that could rewrite our understanding of reality. Picture an endless cosmic ocean, where each bubble floating on its surface is an entire universe, complete with its own stars, galaxies, and perhaps even life. In this bubble multiverse, the laws of physics might not be universal at all. Some bubbles could have stronger gravity, others might lack dark matter entirely, and a few could harbor forces so alien they'd be unrecognizable to us. The question isn't just whether these other universes exist, but what keeps them apart and whether we could ever find proof they're out there. String theory offers one compelling answer. It suggests that higher dimensions, tiny, curled-up spaces far smaller than atoms, could act like invisible walls between universes. Think of it like a stack of papers. Each sheet represents a universe, separated by gaps so thin we'd never notice them. But under the right conditions, these dimensions might vibrate or warp, creating ripples that could theoretically be detected. Some physicists hunt for these ripples in the cosmic microwave background, searching for faint patterns that might betray a collision with another universe long ago. Then there's quantum mechanics, which hints that every decision we make might spawn new realities. In this many worlds interpretation, every possible outcome plays out somewhere in some universe. Mr. Train, somewhere, a version of you caught it, chose a different career. Another you is living that life right now. These branches of reality wouldn't float in space like bubbles. They'd exist alongside ours, separated by an unfathomable quantum divide. The chilling part, we'd never know, because these alternate worlds remain forever locked away like shadows just beyond a mirror's edge. But the most tantalizing clue might come from black holes. Some theories suggest these cosmic voids could be gateways not to other places in our universe, but to other universes entirely. If a black hole's singularity doesn't crush matter into oblivion, but instead spews it out into a new spacetime, our universe might be just one link in an infinite chain. Imagine pouring water into a drain, only for it to reappear in another basin you never knew existed. The implications are staggering. If even one of these theories is true, our universe isn't just vast, it's a single note in a symphony of realities. Civilizations could rise and fall in worlds where chemistry works differently, where time flows backward, or where life takes forms beyond our wildest dreams. And while we may never visit these realms, the mere possibility changes everything. It means the questions we ask about our place in the cosmos might not have one answer, but countless ones, each as real as the last, echoing across the multiverse. What if the universe we perceive, with its galaxies, stars, and vast three-dimensional expanse, is nothing more than a cosmic mirage? The holographic principle turns our understanding of reality inside out, suggesting that everything we see, touch, and experience might be a projection from a two-dimensional surface at the very edge of space. Imagine a movie screen, but instead of flat images, it's generating an entire universe so convincing we'd never suspect it wasn't real. This isn't science fiction. It's a serious theory born from the math of black holes and quantum mechanics, and it hints that the true nature of existence might be hiding in plain sight, just beyond our perception. At the heart of this idea is a startling discovery about black holes. When matter falls into one, it doesn't just vanish. It leaves behind an imprint on the black hole's event horizon, like a fingerprint burned into the fabric of space-time. This suggests that all the information about what's inside the black hole is somehow encoded on its two-dimensional surface. Now, take that concept and scale it up to the entire universe. If a black hole's interior can be described by data on its boundary, could our cosmos work the same way? The holographic principle argues yes, that the three-dimensional world we inhabit is really a projection from a two-dimensional shell at the universe's edge, like a shadow cast by a hidden light. But here's where it gets even stranger. If this is true, then what we call reality might be a kind of cosmic illusion, a simulation running on a surface we can't see or interact with directly. Think of it like a video game. The rich, immersive world you explore on screen isn't actually inside your TV. It's generated by code stored on a chip. In the same way, our universe could be the output of some deeper, more fundamental layer of physics, one that exists not in 3 dimensions but 2. That raises a haunting question. If we're living in a hologram, what or who is the projector? Some theorists speculate that this 2-dimensional boundary might be a kind of cosmic hard drive, storing the information needed to construct our reality at the smallest scales. Every particle, every force, even time itself could be pixels in this grand cosmic display. And just as a hologram can appear 3-dimensional despite being made of flat interference patterns, our universe might emerge from interactions on this distant surface. This would mean that space, as we know it, isn't fundamental, it's an emergent property, like the wetness of water or the heat of a flame. The implications are dizzying. If the holographic principle is correct, then the search for the edge of the universe isn't about finding a physical boundary, it's about uncovering the code that generates reality itself. Experiments are already underway to test this idea, using ultra-precise measurements of quantum entanglement and gravitational waves to look for telltale signs of holographic pixelation in the fabric of space-time. If they succeed, we might finally glimpse the true architecture of existence not as a vast, empty expanse, but as a shimmering surface where every star, every atom, and every thought is just a ripple in something far deeper, far stranger, and infinitely more profound. So is our universe real, or is it a shadow of something greater? The answer might not lie in the stars above us, but in the invisible edges we've yet to discover where dimensions collapse and reality rewrites itself. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, then white holes are their bizarre cosmic opposites. Cosmic fire hoses blasting matter and energy outward with unstoppable force. These theoretical objects, first proposed as mathematical solutions to Einstein's equations, flip the script on everything we know about gravity and space-time. Imagine a black hole in reverse. Instead of an event horizon that traps light forever, a white hole has a boundary that nothing can enter, only escape. It's like trying to swim upstream against a waterfall that's pouring out of nowhere. The idea alone raises wild possibilities. Could white holes be the other end of black holes, funneling matter and energy into distant corners of the universe, or even into other universes entirely? Some theories suggest that every black hole might be connected to a white hole through a wormhole, creating a cosmic tunnel between 2 points in space-time. Picture a drain sucking water down in one universe, only for it to gush back out somewhere else, like a hidden fountain in the cosmic garden. If true, these structures could be nature's ultimate shortcuts, linking regions of reality far beyond our observable horizon. But here's the catch: no one has ever detected a white hole. They might be purely hypothetical, or they could exist in realms so distant or brief that we've yet to spot them. Some scientists speculate that the Big Bang itself could have been a white hole event, a sudden, violent eruption of space and energy from an unknowable source. Others wonder if gamma-ray bursts, those blinding flashes of energy from the depths of space, might be the dying gasps of white holes expelling their final contents. The most tantalizing idea: white holes could be gateways not just to other places but to other times. If matter and light can only exit a white hole, never enter, then anything emerging from one would carry no memory of what came before, like a cosmic reset button. This raises the spine-tingling possibility that what we perceive as the beginning of our universe might just be the aftermath of something older, stranger, and utterly beyond our comprehension. So are white holes real or just a fascinating quirk of mathematics? The answer might lie at the very edge of our universe or beyond it, where the laws of physics as we know them twist into something unrecognizable. Until we find proof, they remain one of cosmology's most thrilling mysteries, a reminder that the universe is far weirder than we've dared to imagine. Einstein once imagined space-time not as a rigid stage, but as a stretchy fabric that could bend, warp, and even fold. That idea gave birth to one of the most thrilling concepts in physics, wormholes, or as scientists call them, Einstein-Rosen bridges. Picture the universe as a vast sheet of paper. Normally, traveling from one side to the other means crossing the entire distance. But what if you could fold that paper, bringing two distant points together and punching a tunnel straight through? That's the promise of a wormhole, a cosmic shortcut linking places that should be impossibly far apart. The math behind these tunnels is rock solid, emerging directly from Einstein's equations. But here's the catch: wormholes are incredibly unstable. The moment one forms, the pull of gravity tries to snap it shut like a rubber band, crushing the tunnel faster than light could travel through it. To keep a wormhole open, you'd need something with negative energy, a substance so exotic it defies everyday physics. Think of it like trying to prop open a collapsing mine shaft with a material that somehow repels gravity instead of succumbing to it. Yet the possibilities are irresistible. If stable wormholes exist, they might not just connect distant stars, they could bridge entirely separate universes. Imagine stepping through a shimmering portal and emerging in a reality where the laws of physics are subtly different, where time flows backward, or where light moves at half its speed here. Some theories even suggest that every black hole might contain a hidden wormhole, a one-way ticket to somewhere or someone else, but the most tantalizing clue comes from quantum mechanics. At the smallest scales, space-time is a seething foam of virtual particles popping in and out of existence. In this quantum froth, microscopic wormholes might constantly form and vanish like bubbles in a boiling pot. Could we somehow harness these fleeting tunnels, stabilizing them long enough to traverse? The answer might lie in the strange world of quantum entanglement, where particles instantly influence each other across vast distances, as if space itself were folding between them. So are wormholes the universe's ultimate cheat code, or just a beautiful mathematical fantasy? For now, they remain a thrilling frontier, a reminder that the cosmos might still hide shortcuts to places beyond our wildest dreams. Between the glittering threads of the cosmic web, where galaxies cluster like cities in the night, lie the universe's great deserts, vast stretches of emptiness so immense they defy comprehension. These cosmic voids can span hundreds of millions of light years, regions where the density of matter drops to near nothing. At first glance, they seem like barren wastelands, the silent gaps in the universe's grand tapestry. But what if these voids aren't empty at all? What if they're hiding secrets that could rewrite our understanding of reality itself? One radical theory suggests these voids might be something far stranger than just empty space. Imagine our universe as a three-dimensional bubble floating in a higher dimensional realm. Now picture other bubbles, other universes brushing against ours. Where they touch, their gravitational influence could create subtle distortions in the fabric of space-time, warping the void regions into invisible gateways. Scientists call these theoretical structures branes, short for membranes, higher dimensional surfaces that could intersect with our universe like sheets of paper passing through one another. In this view, a cosmic void might not be a lack of something, but the presence of something we can't yet perceive. The math behind this idea comes from string theory, which proposes that the fundamental particles of our universe are actually tiny, vibrating strings existing in up to 11 dimensions. Most of these dimensions are curled up so tightly we'd never notice them, but in the depths of a void where matter is scarce and gravity weak, their influence might become detectable. It's like standing in a silent room and suddenly hearing the faint hum of a distant engine, a whisper of something much larger lurking just out of sight. Even more intriguing is the possibility that these voids could be cosmic fingerprints, evidence of collisions with other universes in the distant past. Picture two soap bubbles gently bumping in midair. Where they meet, their surfaces ripple and warp, leaving behind faint imprints. If our universe collided with another long ago, the aftermath might still be visible in the strange, underpopulated regions we call void. Some researchers even hunt for these signatures in the cosmic microwave background, searching for unusual temperature patterns that could betray a brush with another reality. But the most mind-bending implication, if voids are truly gateways to higher dimensions or other universes, then the edge of our observable cosmos might not be the end at all, just a fold in something far grander. Imagine ants crawling across a crumpled sheet of paper. To them, the creases might seem like impassable gaps, but from our perspective, the paper is still connected in ways they can't comprehend. In the same way, these voids could be wrinkles in the fabric of existence itself, hiding pathways to realms beyond our current understanding. So the next time you hear about the emptiness between galaxies, remember, in the cosmos, nothing is ever truly empty. What we call a void might just be the universe's way of whispering that there's more, much more, waiting to be discovered. Somewhere in the depths of space, hidden behind the thick dust clouds of our own Milky Way, lurks a gravitational enigma so powerful it's dragging entire galaxies toward it at breakneck speeds. Scientists call it the Great Attractor, a cosmic siren pulling thousands of galaxies, including our own, through the void at over 14 million miles per hour. But here's the catch: we can't see it directly. Our view is blocked by the very stars and dust that make up our galactic neighborhood, leaving us to piece together clues about this invisible titan from its gravitational fingerprints. At first glance, the Great Attractor seems like it should be a colossal supercluster, a dense knot of galaxies bound together by gravity, but the numbers don't quite add up. Even the largest known superclusters shouldn't exert this much pull. It's like hearing the roar of an unseen waterfall just beyond a dense forest. You know something massive is there, but the trees obscure its true nature. Some researchers speculate it could be a rare hypercluster, a structure so vast it defies our current models of cosmic evolution. Others wonder if dark matter, the invisible glue holding galaxies together, might be concentrated here in ways we've never observed, warping space-time into a gravitational vortex. Then there's the spine-tingling possibility that the Great Attractor isn't the final destination at all. Recent observations reveal an even larger structure beyond it, dubbed the Shapley supercluster, which might be the true source of this cosmic tug-of-war. Imagine a chain of invisible puppeteers, each pulling the strings of galaxies in a dance we're only beginning to map. But here's where it gets stranger. Some theories suggest these gravitational anomalies could be evidence of something beyond our universe, a neighboring reality exerting its influence from across a dimensional divide. The key to unraveling this mystery lies in the peculiar motions of galaxies. Like leaves caught in a hidden current, their paths trace the shape of forces we can't yet see. Astronomers use radio telescopes to peer through the Milky Way's dust, mapping the distribution of galaxies and the subtle distortions in their light caused by the Great Attractor's pull. Each new observation adds another piece to the puzzle, hinting at a cosmic structure so immense it could redefine our understanding of the universe's large-scale architecture. So is the Great Attractor a cosmic aberration, or a signpost pointing to something far grander? the answer might not just reshape our maps of the universe, it could reveal forces at work beyond the edges of known physics. And as technology advances, allowing us to see through the galactic veil, we may finally uncover what's been pulling us toward the unknown all along. Deep in the quantum foam of space-time, where the fabric of reality flickers like a candle in the wind, lies a phenomenon so subtle it could rewrite the story of existence itself. Quantum fluctuations, tiny, unpredictable ripples in the vacuum of space, are often described as the universe's background static. But what if these fleeting disturbances are far more than cosmic noise? What if they're the sparks that ignite entirely new universes, bubbling into existence beyond the edges of our own? Picture a pot of water on the verge of boiling. Before bubbles form, tiny pockets of vapor flicker in and out of existence, too unstable to last. Now imagine space itself behaves this way, with microscopic universes constantly flickering into being, most collapsing instantly, but occasionally one grows just large enough, just fast enough, to escape annihilation and inflate into a full-fledged cosmos. This isn't speculative fiction, it's a serious theory called eternal inflation, which suggests our universe might be just one accidental survivor in an infinite sea of failed attempts. The math behind this idea is both elegant and staggering. According to quantum mechanics, empty space isn't truly empty. It's a seething ocean of virtual particles that pop in and out of existence, borrowing energy from the vacuum before vanishing again. Normally, these fluctuations balance out, leaving no trace. But under extreme conditions like those in the first moments after the Big Bang, a quantum fluctuation could trigger a runaway expansion, stretching a speck of space-time into an entire universe in less time than it takes to blink. Here's where it gets even wilder. If this process is happening beyond our cosmic horizon, then right now, in regions we'll never observe, new universes could be sprouting like mushrooms after rain. Each might have its own unique physics, some where gravity crushes atoms instantly, others where dark energy rips space apart before stars can form. A rare few might even resemble ours, with just the right constants for life to emerge. The implications are dizzying. If eternal inflation is real, then the edge of our universe isn't a boundary, it's a frontier where reality endlessly reinvents itself. We might be living in one cosmic bubble among countless others, separated by stretches of hyper-inflating space where the laws of physics rewrite themselves anew. This isn't just about parallel worlds, it's about the very nature of existence being a chain reaction with no beginning and no end. So how could we ever prove such a thing? Some theorists search for bruises in the cosmic microwave background, subtle imprints left if our infant universe collided with another. Others study the distribution of galaxies, looking for patterns that might betray a collision with a neighboring bubble long ago. But the most haunting possibility is that we'll never know for sure, that the ultimate structure of reality is forever hidden, leaving us to wonder whether we're alone in the cosmos, or just one note in an infinite symphony of universes, each playing its own untold story. The shape of our universe isn't just a cosmic curiosity, it's the blueprint for everything that exists, from the smallest atom to the farthest galaxy. Picture space as a vast, invisible fabric stretching in every direction. But here's the twist, that fabric might not be flat like a tabletop. It could curve gently like the surface of a balloon or warp outward like a saddle, and these subtle bends hold the key to understanding whether the universe has an edge at all. For decades, scientists have chased an answer to one deceptively simple question. Is the geometry of the universe flat, closed, or open? A flat universe would mean parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees, just like in a high school textbook. But if space curves back on itself in a closed universe, those same lines would eventually meet, like longitude lines crossing at the poles of a globe. Travel far enough in one direction, and you'd theoretically end up right back where you started, as if the cosmos were a gigantic cosmic Möbius strip. Then there's the open universe scenario, where space curves outward in a hyperbolic shape, like an infinite saddle. Here, parallel lines would diverge wildly, and triangles would have angles adding up to less than 180 degrees. In this version of reality, the universe wouldn't just be infinite, it would be expanding faster and faster, racing toward a fate of ultimate dissipation where galaxies are ripped apart by the relentless stretching of space itself. So how do we measure something as intangible as the shape of the cosmos? The answer lies in the afterglow of the Big Bang, the cosmic microwave background. Tiny temperature fluctuations in this ancient light serve as a cosmic ruler, revealing whether space is flat, curved, or warped. When scientists analyzed data from satellites like Planck, they found something astonishing. Within a razor-thin margin of error, the universe appears perfectly flat. But that doesn't necessarily mean it's infinite. A flat universe could still wrap around on itself in complex ways, like a video game world where exiting one edge brings you back in from the opposite side. This raises a haunting possibility. If the universe is closed, the edge might not be a boundary at all, but a gateway back to the beginning. Imagine sailing across an ocean so vast you don't realize it's actually a globe, until one day you spot familiar shores on the horizon. Yet if the universe is truly flat and infinite, the concept of an edge becomes meaningless. There's no boundary, no outside, just an endless expanse of space and time where every possible configuration of matter repeats itself over and over, ad infinitum. The stakes couldn't be higher. A closed universe would eventually stop expanding and collapse in a fiery big crunch. An open one would tear itself apart in a big freeze. And a flat universe, it's poised on a knife's edge, expanding just fast enough to avoid collapse but slow enough to hold galaxies together for now. Whatever the true shape, one thing is certain: the answer doesn't just define the universe. It defines what's possible beyond the limits of our imagination. Imagine our universe as a single page in an endless cosmic book floating alongside countless other pages, each one a complete reality with its own stars, galaxies, and perhaps even life. This isn't poetry, it's the spine-tingling premise of brane cosmology, a radical idea born from string theory that reimagines existence itself. According to this theory, what we call the universe might just be a three-dimensional membrane, or brane for short, drifting through a higher dimensional space we can't perceive. And here's the kicker: other branes could be out there, parallel to ours, separated by dimensions so tiny we'd never notice them until they collide. These collisions wouldn't just be cosmic fender benders. They could be the engines of creation, triggering new big bangs and birthing entire universes from the wreckage. Picture two sheets of paper floating in a breeze, slowly drawn together until bang, they meet, releasing enough energy to spark a whole new cosmos. Some physicists believe this might explain the violent birth of our own universe, not as a singular event, but as one collision in an endless cycle of cosmic rebirth. The echoes of that impact could still linger in the cosmic microwave background, hidden in patterns we're only beginning to decode. But how could entire universes exist just out of reach? Think of ants crawling across a tablecloth. They're aware of length and width, but the concept of height, of a third dimension, is beyond their experience. Now imagine another tablecloth suspended inches above theirs. To the ants, it's invisible, untouchable. But if those cloths were to brush against each other, the ants would feel it as a sudden, inexplicable jolt. In the same way, a collision with a neighboring brane might appear to us as a cataclysmic surge of energy, reshaping reality in an instant. The implications are staggering. If branes drift through higher dimensions, then the edge of our universe might not be an edge at all, just the limit of what we can perceive on our membrane. Other branes could be hovering mere millimeters away in a dimension we can't access, their gravity subtly tugging on ours like invisible puppet strings. Some theories even suggest that dark matter, the mysterious substance holding galaxies together, might be ordinary matter from a nearby brane, leaking into ours through hidden gravitational tendrils. So how do we test such an outlandish idea? The answer might lie in gravitational waves, the ripples in space-time caused by cosmic collisions. If another brane brushed against ours, it could send shock waves through the fabric of reality, leaving faint traces in detectors like LIGO. Others hunt for mathematical fingerprints in the distribution of galaxies or the afterglow of the Big Bang, searching for anomalies that defy conventional physics. The smoking gun could be out there, a cosmic clue hidden in plain sight, waiting to rewrite our place in the multiverse. Brane cosmology doesn't just challenge our understanding of the universe, it shatters the very idea of a singular reality. If it's true, we're not just living in a universe, but on a membrane adrift in a sea of higher dimensions, where other worlds, other versions of everything might be closer than we ever dreamed. The cosmic microwave background isn't just a relic of the Big Bang. It's a cosmic whisper carrying secrets from the very edge of existence. This faint glow, bathing the universe in microwaves, is often described as a baby picture of the cosmos, frozen in time when the universe was just 380,000 years old. But look closer, and the image isn't perfectly smooth. Tiny fluctuations, hotter and colder patches dot the cosmic canvas like brushstrokes from an unseen hand. At first glance, these might seem like random noise, but some scientists believe they could be something far more extraordinary, fingerprints from realms beyond our universe. One of the most tantalizing anomalies is the so-called cold spot, a region of the CMB significantly chillier than its surroundings, stretching nearly 2 billion light-years across. This cosmic bruise defies easy explanation. Some theories suggest it could be a shadow cast by a supervoid, a vast, empty region of space where galaxies are eerily scarce. But even that doesn't fully account for its extreme temperature drop. Another possibility, the cold spot might be a collision scar, a remnant of our universe brushing against another bubble in the multiverse. Picture two soap bubbles gently touching in midair. Where they meet, the surface tension distorts, leaving a subtle imprint. If our universe experienced a similar encounter long ago, the energy from that collision could have left a mark, one we're only now learning to read. Then there's the mystery of the CMB's large-scale asymmetry. The universe at its core should be fundamentally uniform, no preferred direction, no cosmic up or down. Yet the CMB reveals a strange lopsidedness, with one hemisphere slightly warmer than the other. It's as if someone tilted the playing field of the early universe, leaving a gradient we still can't explain. Some researchers speculate this could be evidence of a gravitational tug from another universe, warping the fabric of space-time in ways that subtly skewed the distribution of matter and energy in our own. The implications are staggering. If these anomalies truly are cosmic breadcrumbs leading beyond our universe, then the CMB isn't just a snapshot of our past, it's a window into something far grander. Imagine standing in a hall of mirrors, catching glimpses of reflections that don't quite match your own. The distortions hint at spaces beyond the glass, realities just out of reach. In the same way, the CMB's irregularities might be our first glimpse of the multiverse, a realm where other cosmic bubbles float in an unfathomable sea of higher dimensions. Yet for all the excitement, skepticism remains. The cold spot could still be a statistical fluke, the asymmetry a quirk of cosmic chance. The hunt for answers drives scientists to build ever more precise instruments, from space telescopes mapping the CMB in unprecedented detail to supercomputers simulating countless universes, searching for patterns that match our own. With each new dataset, we edge closer to a truth that could rewrite not just the story of our universe, but the very definition of reality itself. So is the CMB a cosmic Rosetta Stone, encoding messages from beyond the edge? Or are we reading meaning into cosmic static, projecting our hopes onto the universe's oldest light? Either way, the search continues not just for answers, but for the next great question waiting to be asked. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate shredders, tearing apart stars and swallowing light itself. But here's the puzzle that keeps physicists up at night. When matter vanishes into a black hole, what happens to the information it carries? Every particle, every atom, holds data about its properties: spin, charge, mass. According to quantum mechanics, that information can never truly disappear. Yet black holes, by their very nature, seem to erase it completely. This contradiction is the black hole information paradox, and solving it might not just crack one of physics' greatest mysteries, it could unveil secrets about what lies beyond the edge of reality itself. At the heart of this enigma is the event horizon, the point of no return where gravity's grip becomes unstoppable. In the 1970s, Stephen Hawking discovered that black holes aren't completely black, they slowly leak radiation, evaporating over eons until they vanish entirely. But if a black hole disappears, what happens to all the information it swallowed? Hawking initially believed it was lost forever, erased from the universe. This idea sent shockwaves through physics because quantum mechanics insists information must be preserved. It's like burning a book and claiming the story inside is gone. Except quantum rules say the ashes should still contain every word, just scrambled beyond recognition. Enter the holographic principle, a radical idea suggesting that all the information falling into a black hole isn't destroyed. It's encoded on the event horizon's surface, like a cosmic hard drive. Picture a movie projected onto a screen. The three-dimensional images you see are actually stored as flat, two-dimensional data. In the same way, the holographic principle proposes that our three-dimensional reality, including everything swallowed by black holes, might be projected from information stored at the universe's boundaries. If true, the event horizon isn't just a one-way street into oblivion. It's a ledger, meticulously recording every bit of data that crosses it. But how does this connect to what lies beyond our universe? Some theorists speculate that if information is preserved at black hole boundaries, it might escape into other regions of space-time, perhaps even other universes. Imagine tossing a message in a bottle into a whirlpool. From your perspective, it's gone. But what if the whirlpool drains into another ocean entirely, where the bottle washes up intact? In this scenario, black holes could be cosmic portals, funneling information into realms we can't see or touch. The most tantalizing clue comes from quantum entanglement, the bizarre phenomenon where particles remain connected across vast distances, instantly influencing each other no matter how far apart they are. When particles near a black hole's event horizon become entangled with radiation escaping it, they might create a hidden link, a quantum bridge preserving information in ways we don't yet understand. It's as if the universe has built-in fail-safes, ensuring nothing is ever truly lost, just transformed or relocated. So is the information paradox a glitch in our understanding, or a gateway to something deeper? The answer could rewrite not just physics, but our very conception of reality. If black holes preserve information at their edges, then those edges might be more than boundaries. They could be windows, offering fleeting glimpses into whatever lies beyond the cosmic veil. And as scientists inch closer to solving this puzzle, one thing becomes clear: the universe is far stranger, far more interconnected than we ever imagined. If the universe were a grand cosmic play, then dark matter and dark energy would be the invisible stagehands pulling strings, shifting scenery, and shaping everything without ever stepping into the spotlight. Together, these enigmatic forces make up 95% of all existence, yet they leave no trace we can directly observe. We only know they're there because of their gravitational fingerprints, galaxies spinning faster than they should, clusters bending light like cosmic mirages, and the universe itself expanding at an ever-accelerating pace. But here's the real twist: what if their influence doesn't stop at the edge of our observable universe? What if they're the architects of realms we can't even imagine? Take dark matter first. This invisible scaffold holds galaxies together like hidden glue, preventing stars from flying apart as they whirl through space. Without it, our Milky Way would have torn itself to shreds billions of years ago. Yet despite decades of searching, we've never caught a single particle of it. Some theories suggest dark matter could be made of undiscovered particles that barely interact with normal matter, ghosts passing through walls without a whisper. Others propose it might not be matter at all, but a shadow of gravity itself behaving differently on cosmic scales. Imagine tossing a rock into a pond and watching the ripples spread, except in this case, the ripples are there, but the rock is invisible. Then there's dark energy, the even more mysterious force driving the universe apart. Unlike gravity, which pulls things together, dark energy pushes, stretching space itself like taffy. Some cosmologists believe it's the energy of empty space, a cosmic constant woven into the fabric of reality. Others think it might be a dynamic field, evolving over time. But the most radical idea: dark energy could be a sign of something beyond our universe, pressure leaking in from higher dimensions or neighboring cosmic bubbles. Picture a balloon inflating inside a sealed box. As it grows, the pressure inside the box changes, even though the balloon can't see the box exists. Could dark energy be our universe brushing up against something far larger? The eerie thing is, these forces might not just shape our universe, they could define what lies beyond it. If dark matter's gravitational web extends past our cosmic horizon, it could be weaving structures in realms we'll never see. And if dark energy keeps accelerating expansion, it might one day tear space apart so completely that distant galaxies vanish over the edge, leaving us isolated in a shrinking island of visibility. Some models even suggest that dark energy's push could birth new universes in a never-ending cycle of creation and dissolution, like bubbles forming in a boiling pot, each with its own unseen architects. So how do we solve a mystery we can't even see? Scientists are chasing answers with underground detectors, particle colliders, and telescopes mapping the cosmos in unprecedented detail. Every experiment brings us closer to understanding whether these invisible forces are confined to our universe, or if they are threads stitching together a multiverse vaster than we dare to dream. One thing's certain: the darkness isn't empty, it's alive with possibilities. Imagine a universe that stretches forever in every direction, infinite, eternal, and filled with endless possibilities. Now picture this: in the vast cosmic silence, a fully formed brain suddenly flickers into existence, complete with memories, thoughts, and the eerie sensation of being alive. Not attached to a body, not born from evolution, but conjured out of nowhere by pure chance. This is the Boltzmann brain, a thought experiment so bizarre it challenges everything we think we know about reality, consciousness, and our place in the cosmos. The idea comes from 19th century physicist Ludwig Boltzmann, who proposed that in an infinitely old and vast universe, even the most improbable events must happen eventually. Given enough time, random quantum fluctuations could assemble atoms into any configuration, including a self-aware mind that pops into existence, believes it has a past, and then vanishes just as quickly. These hypothetical observers wouldn't be products of biology or evolution. They'd be cosmic accidents, brief sparks of awareness in the void, questioning their own existence before dissolving back into chaos. Here's where it gets even stranger. If Boltzmann brains are possible, they should vastly outnumber ordinary, biologically evolved minds like ours. After all, it's far easier for randomness to assemble a single floating brain than an entire universe with galaxies, planets, and life. So why does it feel like we're the real ones? Statistically, the odds suggest we might be the Boltzmann brain's fleeting illusions convinced we're living in a coherent world. It's like waking up in a dream, utterly convinced it's real, only to realize you're just a momentary glitch in the fabric of existence. Some physicists dismiss the paradox as a reductio ad absurdum, a sign that our assumptions about infinity or quantum fluctuations must be flawed. Others see it as a clue that the universe isn't infinitely old, or that some fundamental law prevents such freak occurrences, but the most unsettling possibility. Boltzmann brains could actually exist, drifting beyond our cosmic horizon in the infinite dark, each one a lonely witness to its own brief, fabricated reality. So how do we know we're not one of them? The answer might lie in the consistency of our experience. Boltzmann brains would lack stable, coherent memories or a continuous existence. They'd be flashes of confusion, not beings with lifetimes of accumulated knowledge. The fact that we observe a universe governed by laws with a traceable history and predictable patterns suggests we're part of something real, not just statistical noise. But the paradox lingers like a shadow at the edge of thought, reminding us that in an infinite cosmos, even the wildest possibilities might be waiting just out of sight. Whether a philosophical curiosity or a genuine cosmic mystery, the Boltzmann brain forces us to confront the fragility of our own perception. After all, if reality can be simulated by chance, how can we ever be certain of what's truly out there, or who's truly in here? The universe might hold more surprises than we've dared to imagine. What if everything you've ever known, every touch, every sunrise, every heartbeat, was just lines of code in an unfathomably advanced simulation? The simulation hypothesis isn't science fiction anymore. It's a serious debate among physicists and philosophers. At its core, the idea suggests our universe might be an artificial construct, a digital reality created by some higher intelligence. But here's the spine-tingling question. If we're living in a simulation, what exists outside of it? Is there a vast, unfiltered reality where our creators reside? Or perhaps an infinite stack of simulations within simulations, like cosmic Russian nesting dolls? The argument hinges on a startling possibility. If a civilization could one day create simulations indistinguishable from reality, the odds suggest we're far more likely to be inside one than in the original universe. Think of it like video games. Early graphics were blocky and unrealistic, but today's games approach photorealism. Given enough time, wouldn't a sufficiently advanced civilization build simulations so perfect the inhabitants never suspect they're artificial? If that's true, then statistically, there are probably trillions of simulated minds for every real one, making it vanishingly unlikely we're at the top level of reality. But the real mystery lies beyond the simulation's edge. If our universe is a program, it must run on something, some kind of hardware in a higher reality. Picture a computer so powerful it simulates every atom, every quantum fluctuation in an entire cosmos. What would that machine look like? Where would it exist? Some theorists propose that the outside could be a universe with entirely different physics, where our concept of space and time doesn't even apply. Others imagine a civilization so advanced they've transcended biology, existing as pure energy or information, with godlike control over simulated realities. Then there's the eerie possibility of nested simulations. If a civilization can create one simulated universe, why not billions? Each simulation could contain beings who create their own simulations, leading to an infinite regression of realities. In this scenario, the edge of our universe might just be the limits of our processing power, a firewall preventing us from seeing the deeper layers. It's like a character in a video game trying to perceive the computer it's running on. The system simply isn't designed to let them look outside the screen. The most tantalizing clue might come from glitches. If we're in a simulation, imperfections in the code could reveal themselves tiny anomalies in the fabric of reality. Some scientists have even proposed experiments to test this, like searching for pixelation in the cosmic microwave background or mathematical patterns in quantum mechanics that suggest underlying programming. Others argue that phenomena like quantum indeterminacy, the inherent randomness of particles, might be evidence of computational limits, like a processor skipping calculations to save resources. But here's the twist: even if we prove we're in a simulation, the question of what's beyond remains. Is the outer reality a vast, bustling universe of simulated worlds? Or is it something stranger, a dimension where time flows backward, or where thought alone shapes matter? The simulation hypothesis doesn't just challenge our understanding of reality, it redefines the very meaning of existence. And whether we're living in a cosmic computer or not, one thing is certain: the universe or the program holds mysteries we've only begun to unravel. Time flows forward like an unbreakable rule, a river carrying us from past to future with relentless certainty. But why the secret might lie at the very edge of reality itself. Physicists call this the arrow of time, and its direction isn't just a quirk of perception, it's woven into the fabric of the cosmos. The strange part, this arrow seems tied to the universe's expansion, as if time's flow is stitched into the stretching of space. Picture a deck of cards scattered across a table. Once they're mixed, they'll never spontaneously rearrange into their original order. That's entropy, the universe's tendency toward disorder, and it's the engine driving time's one-way march. Now here's where the edge of reality comes in. If the expansion of space dictates time's arrow, what happens in regions where that expansion behaves differently? Beyond our cosmic horizon, where the rules of physics might warp or break, could there be pockets where time flows backward? Imagine a bubble universe where entropy decreases instead of increases. In that realm, broken teacups might reassemble themselves, smoke would pour back into chimneys, and memories of the future could feel as real as recollections of the past. It sounds like science fiction, but the math doesn't rule it out. The key lies in the Big Bang's aftermath. Our universe began in a state of incredibly low entropy, a pristine, ordered starting point that set the arrow in motion. As space expanded, entropy skyrocketed, creating the asymmetry that makes time feel irreversible. But if other universes were born with different initial conditions, their arrows of time might point in any direction. Some could even loop, cycling through creation and destruction like a cosmic Ouroboros eating its own tail. This raises a haunting possibility. If we could peer beyond the edge of our universe, we might witness realities where cause and effect are reversed. A place where stars collapse into nebulae, life grows younger instead of older, and history unfolds in rewind. The unsettling question isn't just whether such realms exist, but whether they could ever brush against our own, sending echoes of backward causality rippling into our timeline. For now, these ideas remain locked in equations and thought experiments, but they remind us that time, like space, might not be universal. Beyond the edge, the rules could change, and with them, the very nature of existence itself. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars and planets. Given those staggering numbers, the cosmos should be teeming with life. Civilizations older and more advanced than ours, their signals crisscrossing the void. Yet when we listen, all we hear is silence. This eerie contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent life is common, why haven't we found a single trace of it? The answer might lie not in the stars themselves, but in the mysterious boundaries of our own perception. One possibility is that advanced civilizations are deliberately hiding, staying quiet to avoid detection. Think of it like a dark forest, a concept from science fiction where every civilization fears revealing its location, lest it attract something dangerous. If true, the universe could be full of life, all of it whispering in the shadows, wary of drawing attention. Others suggest that technological societies might not last long enough to make contact, burning out in self-destruction or resource collapse before they can spread beyond their home systems. It's a grim thought. Perhaps intelligence is its own greatest threat, a fleeting spark in the cosmic night. Then there's the staggering scale of space itself. Even if civilizations exist, the distances between stars are so vast that communication could be impossible across the gulfs of time. A signal sent from a planet 1,000 light-years away would take a millennium to reach us, longer than the lifespan of most human civilizations. By the time we hear it, the senders might already be gone. Or worse, our own transmissions could be vanishing into the void, unanswered not because no one's there, but because the universe is simply too big for a conversation. But the most unsettling answer might be that we're alone, that life, or at least intelligent life, is vanishingly rare. The conditions needed for complex civilizations to arise could be so precise, so fragile, that Earth is a cosmic fluke. Imagine a desert stretching endlessly in all directions with only a single oasis. If that's the case, the silence isn't just eerie, it's profound. It means the universe is ours to explore, but also ours to lose. Yet there's another, even wilder possibility. What if we have been contacted, but we're just not equipped to recognize it? An advanced civilization might communicate in ways we can't yet comprehend using neutrinos, quantum entanglement, or structures hidden in the fabric of space-time itself. Their messages could be all around us, woven into the background radiation or the orbits of distant stars, waiting for us to develop the eyes to see them. The Fermi Paradox doesn't just ask where the aliens are, it forces us to confront the limits of our own understanding. Are we missing something fundamental about the universe? Or is the silence a message in itself, telling us that the cosmos is stranger, lonelier, or more dangerous than we've dared to imagine? Until we know for sure, the question lingers like a whisper in the dark: are we truly alone? In October 2017, astronomers spotted something extraordinary, a strange, elongated object hurtling through our solar system at blistering speeds. Named Oumuamua, Hawaiian for scout or messenger, it was the first confirmed visitor from interstellar space. But this wasn't just any asteroid or comet. Its bizarre behavior sparked debates that still ripple through the scientific community. The more researchers studied it, the stranger it seemed. Unlike typical comets, Oumuamua showed no signs of a tail as it passed the sun. Its shape, a tumbling, cigar-like structure roughly 10 times longer than it was wide, was unlike anything naturally occurring in our solar system. And then came the real shock. As it raced away, it accelerated slightly, as if pushed by an unseen force. This unexpected acceleration sent imaginations and theories soaring. Normally, comets speed up due to outgassing, the release of gas and dust as they warm near a star. But Oumuamua left no visible trail of debris. Some scientists proposed exotic explanations, like hydrogen ice sublimating invisibly in the vacuum of space. Others, including Harvard astrophysicist Avi Loeb, raised a far more provocative idea. What if Oumuamua wasn't a natural object at all? Could its odd shape, lack of a coma, and unexplained acceleration be signs of artificial origin, a relic from an advanced civilization? The concept isn't as outlandish as it might sound. Humanity has already launched objects into interstellar space, like the Voyager probes. If another civilization did the same, their technology might appear just as perplexing to us as ours would to an alien observer. Oumuamua's unusual trajectory could suggest it wasn't merely drifting, it might have been maneuvering. Some even speculated it could be a solar sail, a thin, reflective structure propelled by sunlight, a technology we're only beginning to explore. Skeptics, of course, argue that extraordinary claims require extraordinary evidence. No radio signals or other signs of technology were detected from Oumuamua. Its acceleration, while unusual, could still have natural explanations we haven't yet uncovered. After all, this was our first close look at an interstellar object. Our sample size of one leaves plenty of room for surprises. Yet the possibility lingers like a thrilling thought experiment. If Oumuamua was artificial, what does that imply about the universe beyond our cosmic neighborhood? Are there other artifacts drifting between the stars, remnants of civilizations that rose and fell long before Earth formed? Or could Oumuamua have been deliberately sent, a message in a bottle, or even a scout probing our solar system? The truth is, we may never know for sure. Oumuamua is already too far away, vanishing into the depths of space. But its brief visit left an indelible mark on astronomy, forcing us to confront how little we understand about what might be lurking in the vast, uncharted territories beyond our solar system. Whether natural or artificial, Oumuamua serves as a humbling reminder. The universe is far stranger and far more mysterious than we've dared to imagine. The universe hums with energy stars burning, black holes spinning, galaxies swirling in an endless cosmic dance. But what if somewhere out there, civilizations have learned to harness that energy on scales we can barely comprehend? This is the promise of the Kardashev scale, a visionary framework that classifies civilizations not by their politics or culture, but by their ability to command the power of the cosmos itself. At the lowest end, Type I civilizations like the one we're struggling to become can harness all the energy of their home planet. Type Roman II civilizations control their entire star, building megastructures like Dyson spheres to capture every photon of sunlight. But it's Type Roman III that truly defies imagination, a civilization capable of wielding the energy of an entire galaxy, bending stars and black holes to their will like gods of physics. The unsettling question isn't just whether such civilizations exist, it's why we haven't found a single trace of them. The Milky Way alone contains over 100 billion stars, many older than our sun by billions of years. If even a handful of civilizations reached Type Roman II or Roman III status in that time, their signatures should be unmistakable. Dyson spheres would blot out stars in infrared, and galactic engineering projects would warp the fabric of space-time itself. Yet our telescopes scan the heavens in vain, finding only silence and starlight. one chilling possibility. These civilizations might be thriving just beyond our cosmic horizon, their light and signals trapped forever outside the observable universe by the relentless expansion of space. Imagine standing on the shore of an endless ocean, watching the horizon curve away into mist. No matter how far you sail, new waters always lie just out of view. In the same way, the accelerating expansion of the universe creates an ever-growing boundary beyond which galaxies, and any civilizations they might harbor, are vanishing over the edge faster than their light can reach us. A type Roman 3 civilization could be orchestrating the dance of stars 100 billion light-years away, and we'd never know, severed from them by the irreversible stretching of space-time. But there's another, even stranger idea. What if advanced civilizations choose to be invisible? A society that masters galactic-scale energy might also master stealth, cloaking their activities to avoid detection. Perhaps they've transcended physical forms, uploading their consciousness into quantum substrates or higher dimensions, leaving no trace we'd recognize. Or maybe they've learned the universe is more dangerous than we realize, and silence is survival. Like hunters in a dark forest, they stay hidden, wary of what else might be listening. The Kardashev scale doesn't just measure energy, it measures the gap between what we know and what might be possible. Standing on the threshold of Type I, we're like ants gazing up at a skyscraper, unable to fathom the minds that built it. Yet the scale also offers hope. If civilizations can ascend to such heights, then the universe, for all its silence, might still be alive with intelligence, just waiting for us to grow wise enough to see it. The universe is barreling toward one of two possible fates: a fiery collapse or an icy, endless drift. On one side, there's the Big Crunch, a cosmic doomsday where gravity finally wins the tug of war against expansion, pulling every galaxy, star, and atom back into a single, searing point. Picture the Big Bang in reverse, space crumpling like a burning piece of paper, time itself folding inward until reality becomes a singularity once more. But here's the twist: some theories suggest this collapse might not be the end. Instead, it could be a reset button, a cosmic rebirth where the crushing density triggers another Big Bang, birthing a brand new universe from the ashes of the old. It's the ultimate phoenix story, written in the language of physics, a cycle of destruction and creation playing out on scales beyond human comprehension. On the opposite end lies the Big Freeze, a far quieter but no less haunting destiny. In this scenario, dark energy keeps stretching space until galaxies vanish over the horizon, stars burn out, and even black holes evaporate into faint whispers of radiation. The universe doesn't end with a bang, but with a whisper, an endless, deepening cold where matter itself decays into nothingness. Time loses all meaning when there's no change left to measure, no energy left to fuel even the smallest motion. Reality becomes a static, frozen wasteland, stretching eternally into the dark. Yet the most unsettling question isn't about the fate of our universe, it's about what lies beyond it. If the Big Crunch births a new cosmos, does that cycle continue forever? Are we just one link in an infinite chain of universes, each with its own laws, its own stories? And if the Big Freeze wins, does the void eventually birth new fluctuations, new sparks of existence from the quantum foam? Some theories suggest that even in the deepest freeze, random quantum events could, given enough time, spawn entirely new Big Bangs, like embers flaring to life in a sea of ash. The answer might lie in the shape of the cosmos itself. If space curves back on itself like the surface of a sphere, the Big Crunch becomes inevitable. But if it's flat or saddle-shaped, the Big Freeze awaits. For now, the evidence leans toward eternal expansion, but the universe has a way of surprising us. Whatever the outcome, one thing is certain. The edge of reality isn't just a boundary, it's a doorway, leading either to rebirth or to the longest, coldest night the cosmos has ever known. Quantum entanglement is one of the most baffling phenomena in physics, a connection so profound it made even Einstein uneasy, calling it spooky action at a distance. Here's how it works. When two particles become entangled, their properties remain mysteriously linked, no matter how far apart they travel. Measure one, and its partner instantly reacts, as if they share a hidden communication channel that defies the speed of light. This isn't just a laboratory curiosity, it's a fundamental feature of reality that challenges our deepest assumptions about space, time, and the nature of the universe itself. Imagine tossing a pair of dice that always land on matching numbers, even if one is on Earth and the other on a planet light years away. That's entanglement in a nutshell, a correlation so perfect it can't be explained by chance or any known force. Experiments have confirmed this phenomenon over and over, with particles separated by hundreds of miles still responding in perfect sync, the strangest part. This connection happens instantaneously, seemingly bypassing the universe's speed limit, the speed of light. Einstein's theory of relativity insists nothing can travel faster than light, yet entanglement appears to do just that, leaving physicists scrambling for explanations. One possibility is that entangled particles aren't truly separate at all, but remain part of a deeper, hidden unity, like two ends of an invisible thread stretching across the cosmos. In this view, what we perceive as vast distances might be illusions, with reality fundamentally interconnected in ways we don't yet understand. Some theories suggest this could hint at extra dimensions, where particles are closer than they appear in our three-dimensional world. Others propose that entanglement reveals a holographic universe where all information is stored at its boundaries, making every particle part of a grand cosmic code. Even more radical is the idea that entanglement might not be confined to our universe. If space-time is just a local construct, could entangled particles be linked across multiple universes, their fates intertwined through higher dimensional bridges? It's a concept straight out of science fiction, yet it emerges naturally from certain interpretations of quantum mechanics. In this scenario, what we call spooky action might actually be evidence of a multiverse, with particles whispering to each other through realities we can't perceive. The implications are staggering. If entanglement transcends our universe's limits, it could mean that the edge of reality isn't a barrier at all, just a fold in something far larger and more interconnected. Perhaps the universe isn't a collection of isolated objects, but a vast, shimmering web where every particle, every star, and every galaxy is subtly linked in ways we're only beginning to glimpse. And if that's true, then the greatest mysteries of existence might not lie in the distant cosmos, but in the invisible threads stitching it all together. The universe shouldn't exist, at least not the way we know it. Every fundamental force, every constant, every delicate balance in nature seems precisely calibrated to allow life to emerge. Tweak gravity by a fraction and stars wouldn't form. Adjust the strong nuclear force slightly, and atoms would never hold together. Even the expansion rate of space itself is fine-tuned to a precision of 1 part in 10 to the 60th power, a number so incomprehensibly small it's like threading a cosmic needle blindfolded. This eerie perfection is the heart of the anthropic principle, the idea that the universe appears tailor-made for life because, well, we're here to observe it. But how did this razor's edge precision come to be? One explanation borders on the philosophical. If the constants weren't just right, we wouldn't be around to question them. It's like a puddle marveling at how perfectly its hole fits its shape. Yet this answer feels unsatisfying, a cosmic shrug to one of existence's deepest mysteries. Enter the multiverse theory, a radical alternative that flips the script. Imagine an infinite froth of universes, each bubbling into existence with its own random set of physical laws. Most would be stillborn, collapsing instantly, or expanding so fast matter never coalesces. But in a tiny fraction, the numbers align by sheer chance, allowing galaxies, planets, and eventually life. We don't live in a designed universe, we live in the lottery winner, the one in a trillion fluke where conditions were just right. The implications are staggering. If the multiverse is real, then beyond our cosmic horizon, there could be realms where gravity crushes atoms in seconds, where time flows backward, or where dark energy rips space apart before the first star flickers to life. These universes might outnumber ours by unimaginable margins, their barren landscapes a silent testament to how rare and fragile our existence truly is. Yet the anthropic principle isn't just about cosmic dice rolls. Some scientists propose a middle ground. What if the laws of physics aren't arbitrary, but emerge from deeper, undiscovered principles? Think of ice crystals forming in water. Their intricate patterns aren't random, but arise from underlying molecular forces. Similarly, our universe's constants might not be fine-tuned at all, but the inevitable outcome of a grander theory we've yet to uncover. String theory, for instance, suggests higher dimensional vibrations could dictate the values we observe, making life not a lucky accident, but a mathematical inevitability. So is the universe fine-tuned for life, or are we just the lucky winners of a cosmic lottery? The answer might lie beyond the edge of our observable cosmos, in realms where the rules rewrite themselves endlessly. Until we know for sure, one thing is certain: the very fact that we can ponder these questions is a miracle, whether by design, chance, or something stranger still. What if the Big Bang wasn't the beginning, just the latest chapter in an endless loop of cosmic death and rebirth? Cyclic Cosmology paints a breathtaking picture of universes endlessly expanding and collapsing, like a cosmic heartbeat pulsing across eternity. In this view, our universe is just one in an infinite series, each ending in a fiery big crunch only to be reborn in a new Big Bang moments later. But here's the mind-bending question: what happens between those cycles? If universes collapse and re-emerge, where do they go when they're not here? Imagine a pendulum swinging through the darkest void. At one extreme, the universe is a searing hot singularity, packed with all matter and energy. As it swings outward, space expands, galaxies form, and time unfolds. Then gravity pulls it all back, reversing the arrow of time until everything collapses again. But unlike a pendulum fixed to a ceiling, this cosmic swing might be moving through something far stranger, a metaspace beyond our dimensions, a realm where the rules of physics as we know them don't apply. Some theorists suggest this metaspace could be a higher dimensional landscape, a sort of cosmic incubator where universes bud off like bubbles in a boiling pot, each with its own unique laws and constants. The math behind cyclic models is surprisingly elegant. By tweaking Einstein's equations, physicists can describe a universe that bounces instead of ending. Quantum effects near the moment of collapse could generate enough repulsive force to reverse the crunch into a bang, recycling the cosmos like a phoenix rising from its own ashes. But the real mystery lies in what carries over between cycles. Could traces of previous universes linger in the fabric of space-time like cosmic scars? Some models suggest that black holes might survive the bounce, their immense gravity punching through the singularity to seed new structures in the next cycle. Others propose that quantum information, the fundamental code of reality, might persist, meaning each universe inherits a faint echo of its predecessor. Then there's the haunting possibility that we're not alone in this meta-space. Other universes might be cycling alongside ours, like pendulums swinging out of sync. If higher dimensions exist, these parallel cycles could brush against one another, leaving imprints in the cosmic microwave background or distorting the large-scale structure of galaxies. Some researchers even speculate that dark energy, the mysterious force accelerating our universe's expansion, could be a sign of this impending collision, a cosmic drumroll before the next bounce. But the most profound implication, if cyclic cosmology is true, time itself might be an illusion. Without a true beginning or end, the arrow of time could be a local phenomenon, a quirk of our current cycle. In the metaspace, the distinction between past and future might dissolve, making our universe's history just one thread in an infinite tapestry of causality. The Big Bang wouldn't be a creation story, just a turning point in an eternal dance. So is the universe a one-time event or a single note in an endless symphony? The answer might lie in the voids between cycles, where reality resets and the cosmos takes its next breath. Until we find proof, the cycle remains a tantalizing possibility, a reminder that the greatest mysteries aren't just beyond the stars but beyond time itself. Exotic matter sounds like something ripped from the pages of a sci-fi novel, a substance so strange it defies the laws of physics as we know them. But this isn't fantasy. It's a theoretical possibility that could hold the key to breaching the very edge of the universe. At its core, exotic matter is hypothesized to possess negative energy density, meaning it repels rather than attracts through gravity. Picture a rubber sheet stretched taut, place a bowling ball on it, and it bends downward. Now imagine a material that pushes the sheet upward instead. That's the bizarre effect exotic matter could have on the fabric of space-time, warping it in ways ordinary matter never could. This isn't just about bending the rules, it's about rewriting them. One of the most tantalizing applications of exotic matter lies in the concept of Alcubierre drives, theoretical warp engines that could contract space-time in front of a spacecraft while expanding it behind, effectively creating a bubble that moves faster than light without violating relativity. The catch: such a drive would require gargantuan amounts of negative energy, precisely the domain of exotic matter. If harnessed, this technology wouldn't just take us to the stars, it could propel us past the cosmic horizon into regions of space currently receding faster than light can chase them. But how could such a substance exist? Quantum mechanics offers a glimmer of possibility. In the quantum vacuum, particles flicker in and out of existence, borrowing energy from nothingness in fleeting violations of conservation laws. Under specific conditions, this Casimir effect generates measurable negative energy between closely spaced plates. It's a microscopic hint that nature might permit the exotic, if only on vanishingly small scales. The challenge: scaling this phenomenon up to cosmic proportions, where even a single gram of exotic matter could require energy equivalent to annihilating Jupiter. The implications of cracking this puzzle are staggering. Beyond enabling warp travel, exotic matter could stabilize wormholes, those hypothetical shortcuts through space-time. Normally, wormholes would snap shut instantly, crushed by their own gravitational forces. But line one with exotic matter, and it might just stay open long enough to traverse, a doorway not just to distant stars, but to other universes or epochs. Some theories even suggest that exotic matter could be the hidden ingredient behind white holes, the theoretical opposites of black holes, spewing matter and energy into our cosmos from who knows where. Yet the greatest mystery isn't how to find exotic matter, it's what lies beyond the edge if we do. If we could warp space-time to reach the cosmic horizon, would we find a void? A multiverse, or something beyond human comprehension? The universe has always been stranger than we imagined. Perhaps the fuel to explore its furthest frontiers is stranger still. Our brains are exquisitely tuned instruments, but tuned for survival, not universal truth. We perceive only a razor-thin slice of reality, like creatures living on the ocean floor who have never imagined sunlight or rain. Our eyes detect just a fraction of the electromagnetic spectrum. Our ears catch only certain vibrations, and our very concept of space and time may be hopelessly provincial. Take something as fundamental as dimensions. We move through 3 of space and 1 of time, but what if there are others, curled up like microscopic origami all around us? To a hypothetical being that perceives 10 dimensions, our entire universe might look as flat and limited as a stick figure drawing. Consider the humble tick, an organism that detects its world through body heat and the scent of butyric acid on mammalian skin. To a tick, these sensations are reality. It has no framework to comprehend cities, symphonies, or the cosmic microwave background. In the same way, our finest telescopes and particle colliders might be like tick sensors, probing only what our particular biology and technology allow. The universe could be teeming with phenomena that don't interact with matter, energy, or forces as we know them, leaving them forever outside our perceptual reach. This isn't just philosophical speculation. Physics already hints at realms beyond our grasp. Dark matter outnumbers normal matter 5 to 1, yet it passes through our bodies like ghosts through walls. We know it's there only by its gravitational shadow. Dark energy, driving the universe's accelerating expansion, is even more elusive, a force with no particle, no mechanism, just an effect we can't explain. These aren't just gaps in our knowledge, they're glaring signs that reality operates on levels we're not equipped to access. Then there's the eerie world of quantum mechanics, where particles exist in multiple states until observed. A reality so counterintuitive that even Einstein rebelled against it. At that scale, causality blurs, time loses meaning, and objects separated by light years remain mysteriously linked. If the quantum realm feels alien, it's because our brains evolved to track medium-sized objects moving at medium speeds. We're prisoners of our own perceptual niche, like fish trying to comprehend fire. The limits run deeper than physics. Our very cognition may be constrained. Imagine explaining a rainbow to someone born blind. No analogy can bridge that gap. Similarly, dimensions beyond our perception, forces that don't interact with our bodies, or even entirely new classes of existence, might be fundamentally unthinkable to human minds. Our tools extend our senses, but they're still built on the same underlying logic. A telescope reveals more stars, not new colors beyond the spectrum. A particle collider smashes known matter, not substances from alternate realities. Yet history offers glimmers of hope. Each scientific revolution, from Copernicus displacing Earth from the universe's center to quantum physics shattering Newton's clockwork, has forced us to accept that reality is stranger than we imagined. The pattern suggests that our current blind spots, too, might one day be illuminated. Perhaps future technologies will let us see dark matter, or new mathematics will unveil hidden dimensions. Or perhaps the universe's full nature will forever dance just beyond the edge of understanding, a reminder that some mysteries aren't puzzles to be solved, but horizons to be marveled at. In the end, the greatest discovery might be this: the universe isn't obliged to make sense to us. Its truths exist independent of our ability to perceive them, and that's what makes the quest so thrilling. The edge of the universe isn't just a physical boundary, it's a mirror reflecting humanity's deepest questions about existence itself. philosophers have wrestled with the concept of limits for centuries, not just as barriers, but as invitations to wonder. Immanuel Kant argued that the human mind is fundamentally incapable of grasping the true nature of reality beyond our sensory experience. To him, the edge wasn't just where the stars ran out, it was the horizon of human understanding, a line we could approach but never cross. Think of it like a fish trying to comprehend life outside its bowl. The glass isn't just a physical barrier but a cognitive one. Yet paradoxically, these limits ignite our curiosity. The unknown doesn't just frustrate us, it fascinates us. Modern thinkers like Thomas Nagel have likened the cosmic horizon to the edges of a map marked, "Here be dragons." The phrase wasn't just a warning, it was an irresistible lure for explorers. In the same way, the boundary of our observable universe isn't a dead end. It's a challenge, daring us to imagine what lies beyond. Some philosophers suggest that the very act of confronting these limits reshapes how we think. The edge becomes a mental workshop where we forge new ideas, from multiverses to higher dimensions, not because we have evidence, but because the mystery demands creativity. This tension between knowledge and the unknowable raises a profound question. Does the edge of the universe exist out there, or is it a construct of our own minds? Phenomenologists like Edmund Husserl would argue that reality is always filtered through human consciousness. The edge isn't an objective line in the cosmos, it's a concept shaped by our tools, our math, and our collective imagination. Ancient cultures saw the sky as a solid dome. Later, it became an endless void. Today, it's a quantum foam bubbling with potential. Each era's edge reflects not just scientific progress, but the evolving boundaries of what we believe is possible. Then there's the existential perspective. For thinkers like Jean-Paul Sartre, the void beyond the edge isn't just empty space, it's a metaphor for the absurdity of existence. In a universe without inherent meaning, the edge becomes a blank canvas where we project our hopes, fears, and myths. Some see it as a warning, a reminder of our cosmic insignificance. Others find liberation in its vastness, a sign that we're free to create our own purpose. The edge, in this light, isn't just a place, it's a Rorschach test for the human condition. Perhaps the most radical view comes from panpsychism, the idea that consciousness is a fundamental feature of reality. If true, then the edge isn't a barrier between here and there, but a seamless transition in a universe that's alive and aware at every scale. The void beyond might not be empty at all, just vibrating with forms of intelligence we can't yet recognize. Like ants unaware of the internet, we might be surrounded by layers of reality we lack the senses to perceive. What unites these perspectives isn't answers, but a shared recognition. The edge of the universe is more than a scientific frontier. It's a mirror, a muse, and a mystery, one that tells us as much about ourselves as it does about the cosmos. Every theory, from Kant's limits to quantum multiverses, is ultimately a story we tell to make sense of the darkness beyond the stars. And in that storytelling, we don't just map the universe, we discover what it means to be human, standing on the shore of the infinite. As we stand at the precipice of understanding, gazing into the cosmic unknown, the question of what lies beyond the edge isn't just a scientific puzzle. It's a mirror reflecting humanity's boundless curiosity. For centuries, we've charted the stars, unraveled the laws of physics, and stretched the limits of our imagination, only to find that the universe always has another secret waiting just out of reach. Whether it's the multiverse's infinite variations, the holographic edges of reality, or dimensions folded beyond perception, each theory is a testament to our refusal to accept that the story ends where our telescopes can't see. This journey isn't just about finding answers, it's about the thrill of the chase. Every time we think we've grasped the cosmos, it slips through our fingers like stardust, leaving us with new questions, new mysteries to solve. Think of the explorers who once believed the ocean had an edge, only to discover continents they never dreamed existed. Or the physicists who shattered atoms, expecting simplicity, and found a universe teeming with particles more bizarre than fiction. The edge of our understanding isn't a wall, it's a doorway, and history shows us that the greatest discoveries begin the moment we dare to step through it. But here's the beautiful paradox: the more we learn, the more we realize how much we don't know. Dark matter, dark energy, quantum entanglement, these aren't just gaps in our knowledge. They're invitations to dig deeper, to rethink everything we thought was certain. The universe doesn't owe us clarity, and yet, it's in the pursuit of these enigmas that we've uncovered some of our most profound truths. The Big Bang, black holes, the fabric of space-time, these were once dismissed as wild speculation. Now, they're the foundation of modern cosmology. Who's to say today's wildest ideas won't be tomorrow's textbooks? So what's next? Perhaps one day, a revolutionary telescope will peer beyond the cosmic microwave background, capturing light from realms we can't yet fathom. Or maybe a breakthrough in quantum gravity will reveal hidden connections between universes, like threads in a vast, multidimensional tapestry. Or just maybe, the answer lies not in a device or equation, but in a perspective so radical we haven't even conceived of it yet. That's the magic of science and philosophy. The future is always richer, stranger, and more wondrous than we predict. As we wrap up this cosmic journey, remember, the edge of the universe isn't just a place. It's a call to adventure. Whether you're a scientist, a dreamer, or simply someone who's ever looked up at the night sky and wondered, you're part of this grand exploration. So keep questioning, keep imagining, and most of all, keep reaching for the unknown. After all, the next great discovery might not be hidden in the stars, but in the spark of curiosity that drives us to look beyond them. Don't forget to share your thoughts in the comments below. What do you think lies beyond the edge? And if you enjoyed this journey through the cosmos, be sure to like, subscribe, and join us as we keep exploring the universe's greatest mysteries together. Until next time, stay curious.